Hi, and welcome to my Docent lecture. I am Johnsson from the School of Electrical Engineering at KTH Stockholm. In this presentation, I will talk about my research on radio frequency heating of fusion plasmas. But before I get to the details of my work, I want to give you a brief introduction to fusion energy. So the reaction of interest for a fusion power plant is between the two heavy isotopes of hydrogen called deuterium and tritium. This reaction produces a helium-4 nucleus and a neutron, along with 17.6 mega electron volts of kinetic energy. This is about 1,000,000 times larger than the energy released in chemical reactions. Thus, fusion energy creates huge amounts of energy from very little fuel. So what do we need for fusion reactions to occur? Well, deuterium is abundant in seawater and can easily be extracted. Tritium, on the other hand, is a radioactive isotope with a half-life of about 12 years, so there is no natural tritium on Earth. Instead, it has to be produced in a fusion reactor. To generate tritium, we start from the deuterium-tritium reactions, which produces a neutron. If this neutron is allowed to react with lithium-6 or lithium-7, it produces a new tritium atom. Thus, the fuel needed for fusion comes from seawater and lithium. The supply of these resources is practically limitless. But there is, of course, a catch here. For the reaction to occur, we need 200 million degrees Celsius, which is 10 times hotter than the center of the sun. So how do we create a machine that can confine these temperatures without melting? Well, first, note that at these temperatures, all atoms are ionized, so our gas is turned into a plasma of charged particles. And charged particles can in fact be confined by magnetic fields, since the field line forces the charged particles to gyrate around the field lines. If we now bend the field lines into a ring or a torus, the charged particles, which are gyrating around the field lines, tend to follow the field lines and move round and round the torus without reaching the wall. This allows us to heat the high-density center of the plasma to 200 million degrees, while the plasma edge is relatively cool. In addition, by pumping at the edge, a very low edge density can be achieved, thus reducing the interactions with the wall. This enables us to avoid melting. So now we have the principle of plasma confinement. Next, we need to build a reactor. So experimental research on fusion energy has been around since the 1950s. And the big breakthrough came in the mid-60s with the Russian invention of the tokamak, where the plasma was heated to many millions of degrees. However, soon it became clear that in order to improve the performance, we needed to build bigger devices. So in the 60s, 70s, and 80s, larger and larger machines were built. The largest of these were the JET device. In 1997, JET set the present fusion world record by producing 16 megawatts of energy, which corresponds to 65% of the input power. The next step after JET is the ITER device, which is 8 times larger than JET. It was originally conceived in the 1980s, but after long delays, it's finally being built in southern France. ITER is designed to produce 500 megawatts of fusion power, which is 10 times more power than it consumes. With the knowledge gained from the ITER, the plan is to build an even larger device called DEMO that shall provide electrical power to the grid by 2050. So as a fusion researcher today, one of my main goals is to make reliable extrapolations from the relatively small devices of today to the huge devices of the future. My own research is focused on the modeling of radio frequency heating of fusion plasmas. This work is partly theoretical, but it also includes close collaborations with experiments, both to validate our models and to use these models to prepare experiments and to analyze experiments. Another key component of my research is on integrated modeling. This is a collaborative effort where we bring together state-of-the-art models from different fields and builds a meta-model that can simulate full plasma discharges. The modeling of radiofrequency heating of fusion plasmas combines the modeling of both electromagnetic fields and the kinetic motions of plasma particles. These in turn determines the dielectric properties of the plasma. This problem is really a multi-scale problem, where the fastest timescales related to the wave frequency and the gyro motion is of the order of 100 MHz, while the motion along the field lines have frequencies between 10 and 100 kHz. The collisional relaxation of fast ions can be as slow as 1 Hz. So to solve this problem, we use perturbation theory, an average over the small amplitude fast variations. The result is a new set of equations for the slow dynamics induced by the wave heating and collisional relaxation. To illustrate how we model wave-particle interactions, we start from the wave field. As the wave accelerates particles, the distribution functions of the plasma particles is modified. The new distribution function now determines the conductivity or the dielectric plasma response that describes the wave-induced currents. And wave-induced currents in turn allows us to calculate new electric field. At KTH, we have developed a model called SELFO that solves this problem self-consistently, meaning that the wave damping is consistent with the particle acceleration. To illustrate the use of the SELFO code, we will now look at an instability that appears in practically all high-performance tokamak plasmas, called the sawtooth instability, which is a collapse of the central plasma. In the figure, the sawtooth is illustrated as regular crashes in the soft X-ray emission from the plasma. The sawtooths tend to reduce the plasma performance, but more importantly, larger crashes may cause secondary instabilities. Therefore, it is often better to have frequent mild crashes than fewer large ones. It is therefore important that we can control the sawtooth in a tokamak reactor. And in fact, sawtooth control using radio wave heating has been demonstrated on the jet tokamak, including both stabilization and destabilization. These results were shown to be sensitive to the location where the wave are resonant with the particles, and as well as to the concentration of hydrogen in the plasma. In order to be able to extrapolate this technique to ether, we need a model that can predict this behavior in some detail, including the dependence on the resonance location and the hydrogen concentration. The first step in the modeling is instability criteria. In the inequality shown, we may identify two parameters that may be modified by the radiofrequency heating. Here, the denominator S represents the so-called magnetic shear, while delta W is an energy functional that depends on the sawtooth eigenmode. Initial modeling of these experiments included only the effects of the magnetic shear S. At first, these results seemed promising, as qualitatively many of the relevant features seemed to be there. However, once we acquired the tools to compare quantitatively, the theory did not reproduce the experimental results. Extended modeling was therefore performed using the SELFO code in combination with the so-called Haggis code to calculate also the delta F factor in the instability criterion. The new results were able to predict the control capability, including the sensitivity to both the resonance location and the hydrogen concentration. So once we had a detailed agreement with JET, we applied the same model to see if sawtooth control was achievable on ITER. The modeling showed that the 20 megawatts available on ITER should be sufficient to control the sawtooth. If the power is reduced to 10 megawatt, we still expect to be able to reduce the detrimental effect of the sawtooth instability. So to summarize, fusion energy is a power source with abundant resources, producing 1 million times more energy than chemical reactions. However, this process requires 200 million degrees of Celsius. At these temperatures, we have a plasma that can be confined by a magnetic field, but we need very large devices in order to build a power plant. My work focuses on the modeling of radio frequency heating in fusion plasmas, which involves the coupling of codes describing the wave propagation and the motion of the plasma particles. I've shown you an example where we have successfully modeled sawtooth control in JET, thus validating our theoretical model and bringing a form of enhanced reliability to predictions made for future devices like ITER. Okay, so that's all from me. Thank you for listening to my Docent presentation.